Right. So, salam and good afternoon, all. Can you hear me? Um, can you hear me? All right. So, today we are looking at the third part of your research methodology module that will be um, interestingly entitled research methodology as well. So, we are supposed to be spending this afternoon and also tomorrow's afternoon from 2 to 5. What I've got in mind is that I don't think you want to be stuck with me for two consecutive afternoons. Um, I believe that the slides have been shared with you, so you can refer to that. And I'm hoping that we can cover the slides by today, so that tomorrow afternoon you can use the time to complete your assignment. It's just a very simple assignment. I'll take you through it at the end of today's session. Okay, so just to have some housekeeping done here. One, you have accessed and retrieved the slide. Have you got it? I believe it's being shared on the drive, things like that, for the slides, yeah? Yeah, hi, Jayaraj. Okay, good. Thank you, Nadia, for the response. And number two, I apologize for my voice. Just trying to recover from a bad cold. So, but hopefully, if you can't hear me or I'm not speaking too clearly at any point of time, please let me know. I'll try to repeat myself. Okay, so without further ado, here we go. Let me pull up the slides, and hopefully we have a good session this afternoon. Right. Let's see. I presume that none of you are actually on campus, right? But nonetheless, and most of you will be in your first semester, should be in the first semester, but maybe for various reasons, you may be already in your second semester. So, whatever it is, first and foremost, welcome to UTHM, albeit this may be virtually. And whether you're taking a PhD or master's by research studies, I'd like to wish you all the best. At this very early stage of your studies, try not to worry too much. Just stick closely to your supervisors if you have more than one, and pay more attention to what he or she is telling you to do. Keep up the meetings. When I say meetings, not necessarily to be there face to face, having a formal engagement. It could be something as simple as having a WhatsApp communication at least 2 or 3 times a week, just to keep each other updated on what you're doing, and also to let your supervisor be able to detect if there's any areas that you need help. So what I'm trying to say here is that keep the communication channel open with your supervisor. Never allow it to go stale or to go cold. When the trail goes cold, that is when we start to distance ourselves from our supervisor, and that is not going to be very helpful or even creating a healthy study and learning environment for yourself, especially if you are a working student, right? Which I believe quite a number of you will be in such situations, or either you're working and taking your research studies at the same time, or you are abroad, I mean that you're in your home country or working, and this is considered a part-time task or part-time undertaking for you. So it's very important to stay very um, in close touch with your supervisor and to maintain a good rapport so that he or she can help you throughout the journey. All right. And I'm Chiming. I'm from the Faculty of Engineering Technology of the same of the university, obviously, and I'm based in the Pago campus. If you don't already know, the university has got two main campuses. One is in Batu Pahat, and the other one is in Pago. It's about 45 minutes apart from one another over the expressway. And my background is civil engineering actually, so I do apologize upfront if the examples that I'm going to share with you later on will be more leaning towards civil engineering, right? I've tried to include some examples beyond the civil engineering realm, so hope it's going to be helpful later on. And you can also see that I've added in the term your journey as a subtitle to sharing this afternoon. Well, this is not a lecture, all right? So don't take it as a lecture. It's more like sharing session. You can stop me anytime. If you've got any question or you got something to share. All right. So it's going to be a journey, and let's hope that it's going to be a good one with full support and help from your supervisor and also all your other collaborators if the project involves such. Okay. So here we go. So it's not going to get hang. Okay. Now, what is research? In a tongue-in-cheek manner, you can say that if we knew what we're doing, it wouldn't be called research, would it? Research, and then we research again, right? That is research, and because we don't know the answer, hence there's a problem statement. Hence, we come up with objectives or what we try to identify, what try to resolve, what the questions we try to answer, and we frame our project or research within certain limitations. For example, a certain size, the number of respondents, the people we are targeting to obtain the information, or it could be the locations we are going to collect our samples, and so on and so forth. So all these will boil down to doing a research, and you can already hear the words coming over, like problem statement, project scope, and so on and so forth. All right. And I'll start the ball rolling by having a quick recap, which I believe my the earlier modules have introduced you to this about research. And just a quick recap here. When we talk about doing research, then we cannot escape from talking about research methodology. And briefly, um, research methodology is a structured approach, if you like, a very organized manner, very sequential and logical way that you use to investigate a problem. It is the why and how behind every single one of your research questions. So you can see here that it is a way, if you like, and almost like GPS. Right? If I say map, you probably wouldn't know what a map is now. It's a very obsolete word now. It's not more like a GPS, a global positioning system. To guide, to help us to navigate from one point to another. And why is it typically necessary in engineering studies? Because our work in engineering area is always associated with safety, with cost, performance, and not just for putting on the shelf, but to ensure that it is going to go out to the real world to be for implementation, right, for deployment. Hence, if we have poor planning leading to poor methodology, likelihood is that they're going to get invalid results and leading to what? Leading to answers that are resulting in failure. In other words, we may be doing something the right way, but not quite getting the correct answer. Or we may be doing something the wrong way, and yet we believe it's the right way, and getting certain answers which we believe to be correct and spot on, but they are not quite answering the question and not quite getting the answers using the correct method. So you can see that it is very crucial, yeah, my dear student, to have the correct roadmap, to have the correct GPS settings before we begin the journey. And the core components of research would be the research questions. What exactly do you want to find out? The methods and the tools. We have defined the questions now. How are you going to get the answers? Then those will be depending on the tools and the methods that you select. And then what are the data? What measurements or observations are you going to use when you obtain the data? What about the analysis method? How will you interpret the data? Right? And finally, how do we validate that? How can we be sure that the answers that we're going to report now in the thesis, in the Viva, is correct? All right. So you can see here that it is important to set the groundwork in completion, before we begin the journey of research. Otherwise, it is trying to head to a place, a destination, without having your GPS set. You wouldn't do that, would you? You wouldn't try to come to the UTSM campus for the first time without setting your GPS. So same thing here. You will not embark on your research journey, whether it's a master's or PhD, without having got the settings of your GPS right. And in this case, it's the research methodology. All right. And before we go any further, it'll be good to bear in mind, to remind ourselves as a good researcher that we got to make sure that our work is always well organized and properly managed. So in other words, we are talking about research management. The key concepts are encapsulated in these 10 items here. Quickly, you can see we do planning, we got plan. What exactly are the goals? What are the milestones? When we talk about planning, we start talking about timeline. All right, this is where you start introducing your Gantt charts, probably you use Microsoft projects and all other various freewares and softwares out there to help you keep time and keep track of the progress. Right. Number two, the feasibility. Is the project that I want to execute something that is viable, doable? What are the risks involved? Are the risks so high that the risk level are so high that the likelihood or chances of me getting delayed or even getting the project truncated midway is too high? So these are the considerations you got to make. What about the resources that I have? Not just about labs, equipment, what are the people I can seek advice from? What about external assistance that I need? Are they available? Are they there? Are they accessible? Safety, the work that I'm going to do, do I have enough safety measures in place? All right. For instance, if I were to do an investigation on explosion, for example, then I may have all the equipment, all the devices, all the knowledge, all the skills to settle the explosive, right? Or I may not have enough protection system in the university on campus from the lab facilities, existing facilities to actually contain the explosion. So that is about safety issues. Number five, what are the data? How do I standardize the data collection method? How do I store them? How do I make sure that I can easily retrieve them? How do I make sure that after I process them, analyze them, they are reproducible? Right? If I were to, for instance, simple example, if I were to plot a line graph here on my laptop, when I share it with my supervisor and he or she opens it in his or her PC, it is not going to go all over the place. We know that happens sometimes, right? We send the document to someone, that's why we do PDF. Things are not frozen in place, and it could be doing, hey, it could have on haywire, by that it reaches the other person, right? Number six, what about the methods? What are we going to do? What are the tools we are going to adopt? What are the steps we are going to follow? What are the kind of prescriptive procedures from the standards that we are going to refer to ensure that the questions can be answered via the data that we collect using the methods that we have determined? Number seven, does my work involve collaboration with other people? For instance, it's an industry-based project, then what about my coordination and agreement with the industry? Is there some kind of non-disclosure agreement going on? Or is there some kind of timeline to the tie up to my work progress? For instance, the industry will want the answer in 6 months' time, but according to my work plan for my master's or PhD, in 6 months' time, I wouldn't have reached that stage or that milestone that the industry is expecting, that we need to make some arrangement. We can come to some new agreements there. All right. And it also could be that your work involves or your work constitutes a project, a sub-project to a greater project, a bigger project. All right. Perhaps your supervisor has got a PRGS, prototype grant, meaning that the project is a sub-project to a greater project. Three projects, mini projects, build a big project. So we got to coordinate with other groups, other teams as well to make sure that our work is in line with what everyone is moving towards. There's a greater goal. Number eight, funding. All right, apart from your own scholarship, the grants available, especially if our project or study is expensive. For instance, if it's chemical based, a lot of times the chemical compounds, the substances that we need to acquire can be costly because, for instance, if it's not available locally, you need to source it from abroad. So it takes more time. If we use air freight, it's going to cost more money and stuff like that. Monitoring. How can I make sure that my work is being self-monitored and also enabling my supervisor to help monitor my project securely? Okay. Last but not least, the translational outcome of my research, meaning that how do I move my research outcome into a tangible result. It could be a prototype, it could be a model, it could be an equation. So usually we associate these with IP, intellectual property. It could be something that is being patented, something that is being trademarked and stuff like that. So not necessarily all research will lead to a prototype, not necessarily, okay? Many good projects and brilliant projects end up with a graph, a simple graph, a reference diagram and stuff like that. So many good projects also end up with statements of how to improve the current way of doing things, and yet they give impactful contribution to the field of study. All right. So do not fret about it. Not necessarily that you have to produce a rocket to earn your PhD. It could be a screw, a nut to the propeller of the rocket, which nobody sees. That is your PhD. It could be something as small as that. All right. Okay. And in terms of research design, you see that primarily there are three ways for us to design a project: theoretical framework. So what are the underlying underpinning models, law, principles in our work? For instance, the heat transfer equation to predict how fast the material will actually cool down if your study is in this area. Second, the simulation framework. How can I actually represent, all right? Represent the system out there, all right? Whether it's a plant, factory, or in a natural system like earthquake, digitally, before I run my physical testing. So this is getting more and more popular, I guess, these days in research work, where we try to minimize the risk of running into the hard wall or going down a dead end by doing physical measurements and physical work um, directly, trying to do some simulations before that, prior to the actual modeling, physical modeling, to make sure that we don't get into such situations, roadblocks, and taking up extra time. All right, it could be time consuming, labor intensive, and it could be very demotivating if we do trials and errors physically, and it's tedious and time, and it could be very financially exhaustive as well. Okay, example would be simulating the airflow over a new aerodynamic drone design before actually trying to build a prototype. Okay, and of course, finally, there's always the experimental framework, and we're actually physically testing it though. So this could be creating a small scale prototype to run the test, maybe the wing of a drone, a propeller of it, or it could be taking samples from the site, say you're trying to examine the stabilizing effect of the volcanic ash collected from a certain place. So stuff like that. They require a lot of lab-based examinations. So that would be depending very much on your experimental framework. For instance, measuring the ambient strength or clay soil sample or retrieve from a site. And a lot of times, actually, my students, these three research approach are being intertwined, meaning that you do theoretical, that is almost compulsory, you can say, and you do a little bit of simulation, and then the main work is done experimentally. Or it could be a little bit on experiment, physical experiment, but mainly it is simulation. It really depends on the nature and the scope of your study there. And this integrated approach is very common. For example, if you're trying to design a vibration absorber, so the theory you're going to refer to will be the conventional mass spring damper equations, right? And what are the simulations? You probably model the system using MATLAB, which is a very commonly used software. And the experiment will be I build the prototype and then I measure the vibration reduction and compare it with what I have simulated using MATLAB. And from there, I do the optimization exercise. So as you see, this integrated approach is very common these days because of the more, number one, with the increasing power of our computers, and number two, the availability of softwares these days, the student versions which affordable or could be free online and stuff like that. Okay. Now, we zoom in and look at the research types, and I guess you are already familiar with this, or at least you have heard of it, that the quantitative research, qualitative research, and also the mixed method, right? And for us, for those of us in the engineering area, you see that most of the time, we were dabbling in the quantitative data collection and analysis area. Rarely, a pure engineering project will actually venture into using qualitative method, right? Let alone the mixed method. If your project requires you to do the qualitative method, do make sure that you get the correct guidance and correct background understanding of it before jumping into it. So either your supervisor or your co-supervisor has that aptitude, has that knowledge and ability to help you, or you will really need to seek help from other people. In nutrition, the experts will most probably find the experts in FPTP, FPTV, or the social sciences lecturers. All right. So just a quick reminder, be cautious about that, because we in the engineering arena, we are not very well versed and we are not trained actually to do qualitative research in a general way. Okay. So for quantitative research, we deal with numbers, obviously, and typically these are measurements that we get from simulations, instruments, measurements typically, right? And the sources of these quantitative data could be from sensor reading, right? Performance measurements or simulation outputs. And some common quantitative analysis techniques are, as you can see here, we use descriptive statistics, which we learn even in our secondary school, right? To get the mean, the median, and the deviation. For example, the average battery discharge time across 10 tests, and out of the 10 data that you have collected, do you want to take all 10 for averaging? Or you can find some weird, strange outliers that you need to omit with reasons. Number two, regression. We do that when there is a plot, y-axis, x-axis, these two parameters are correlated. You can see all the data points are scattered, but you can still see a straight line cutting across them. So trying to find a universal relationship between them, like predicting the fuel efficiency based on engine speed, right? Regression analysis. Or you could be doing some statistical analysis with ANOVA hypothesis testing, checking the difference between groups, whether they're significant or not. Like, does adding fiber reinforcement significantly increase the composite strength? So we have run hundreds of 100 samples, and from there, using running an ANOVA analysis, you could tell how confident are you to say that yes, a certain dosage of fibers added to the concrete sample, for instance, will actually increase the strength significantly, and you define what is significantly increased. 10%, 20%, 25%. So these are little things that we need to pay attention to when we are designing our project, right? And last but not least is the error and uncertainty analysis to ensure accuracy. For instance, how would you report a sensor reading? Is the accuracy up to the going up to plus minus 0.5 centigrade, or just 1 centigrade, right? 0.5 and 1, it makes a huge difference, right? So you got to make sure that every equipment that you use to do your measurements, you are assured of two things. One, the accuracy. Two, the calibration. With accuracy, no calibration, there is still no accuracy there. Okay. Next, we look at the qualitative method. It is non-numerical, right? Compared to quantitative, is numbers. However, it explains the context, the behavior, and also the processes. So the sources of data could be from like studying how an operator uses a machine. You can't quantify that, but you can describe that, right? To understand the reasons for a device to be misused or for the failure, you don't really measure anything, but you could be trying observing and study and trying to understand for the device to go into dysfunctional mode. Together user requirements for the system, or what do the operator needs more? Is it some additional safety features, or is it some more ergonomic design of the levers, stuff like that, to analyze the workflow inefficiencies. So you can see here, yeah, things are not quite putting a number to things here, right? These are the qualitative approach time. And some common qualitative analysis techniques include interviews, right? Asking engineers about about the machine downtime causes. What do engineers think as 10 times as a breakdown? I interviewed 5 engineers, and what are their takes on why there's a breakdown. It's not something I quantify, but it's their opinion. Right? Based on observation, I observe on site. I spend 1 hour per shift at the plant to look at the workers working at different shifts. Is there a certain pattern? Is that the morning and the night shift workers tend to be a little bit more careless, whereas afternoon shift workers are more alert? Is it something that is you can't quantify, or you can observe? Document analysis, you could be reading an existing record, a log, maintenance logs, and things like that, and try to identify is there a need and a gap that requires attention for more training, for instance. So I believe that again, so you can see there's a certain pattern emerging here for qualitative research, right? Now, you also probably have heard about this mixed method when I put quantitative and qualitative together. So you get the best of both worlds where the numbers from the quantitative approach will tell you what happens, whereas the qualitative insights will tell you why it happens. Human nature, human failure, the climatic conditions, stuff like that. So you can say that a mixed method will actually integrate the quantitative testing with the qualitative understanding so that engineers can evaluate how well a system works and then why it performs that way. Right? So it's like getting the best of the both worlds. And then an example of mixed analysis technique would be like trying to improve operator performance in the control room. It's more like for the electrical and mechanical engineering students. Quantitative approach-wise, we are looking at measuring reaction time, error rates, frequency of changing the lever position, for instance. Qualitative approach, we are looking at interviewing the operators about the interface difficulties, the safety issues, for instance. When we combine these two approaches, and we find that, yeah, we get the complete picture now. So you could see that mixed methods will actually help engineers create solutions that are not only technically strong, technically viable, they are also aligned with the real-world users' environment and constraints. Often we find a solution is technically sound, nothing wrong with the equipment, nothing wrong with the technical solution. Or people don't use it. It is not suitable for their temperament. It's not suitable for the working environment and things like that. Okay, that's why you can see here a mixed approach has its advantages there. Okay, so that goes the intro. We go quickly now into the data analysis, more on the introduction. Okay, I got to admit right at the beginning here, dear students, that from this point forward, a lot of these analytical approaches that we're going to talk about is focused or revolves around the quantitative approach. Because as I mentioned earlier on, in the engineering field, 90% of our work is actually based on quantitative, if not more. And being no expert, in fact, totally a novice, or not even a novice in qualitative research, that's me, I wouldn't dare to pretend that I know and give you false information, even wrongly guide you. So if your work requires qualitative method in terms of analysis and all, please seek help from your supervisor, your co-supervisors, and also people, experts from the respective fields of study. Okay. So when we talk about data analysis, we almost always relate with statistics, logic, computational techniques, right? So the baseline is that we try to transform raw data into some meaningful information so that it can help us, right, to explain what is happening, to validate a hypothesis, to reveal a certain pattern or trends, and also to guide us to making decisions and to come to a good conclusion. For instance, a researcher wants to study children's achievement in mathematics, so you just can't go in and get the data and say these are the results. No, you got to have the basic information in first, like the gender, the age of the kids, the grade level, what are the grading systems being adopted, and what are the tasks that are being assigned, things like that. And this raw data will then be integrated using specific chosen statistical programs to show the relationship between the different variables that you examine. Okay, and we know these days, this is a very data-driven world. Simple as you want to buy something, we don't need to go to the shop and ask about it. We just Google or ask ChatGPT, even go and search out on, I don't know, Lazada, Shopee, right? To compare prices. You don't even need to step out of the room. Right? So the goal of doing a research, quantitative research especially is to derive actionable insights from data to solve the problem, to make some predictions, and sometimes it's just improve the process, not necessarily to invent or come up with a prototype. It's just an idea, on a validated idea, a well-researched idea on how to improve the processes. Okay, so bearing in mind that quantitative research always involves numbers, right? Very numerical based, and the data got to be accessible and acquirable for us to detect, to inspect questions about the sample population. All right, it gives an answer to your research question, but the sample must be there. Otherwise, it's just posing an empty question. And the way we collect and analyze the data must follow a certain standardized manner. Some reputable, well accepted, well established methodology, so that when we report our findings based on those results that we obtain, they will be credible. In other words, they are trustworthy results. Similarly, you look at the other people's work in the literature, right? When you conduct your literature review, you'll be looking at someone's data and wondering, yes, no. You start the question by, is the data being collected using the correct way, standardized way? If I'm going to emulate this researcher, can I repeat the test or duplicate the test? If the test is being conducted, the measurements were being conducted using a standard that you're not familiar with or you can't comply with, then that paper, the information there is as good as new to you. Okay, so it's as serious as that, right? So the importance of finding a research, obviously, to solve the problem, identify trends, optimize performance, as we mentioned earlier on. So now we zoom into data collection. Is there any questions so far? Half an hour into it, are you sitting down comfortably and listening in all right? Is it okay? Can I continue? Okay. Thank you, Zul, Raihan, Ahmad, Agla, for the response. So we move on to data collection here. Now, data collection is really about gathering information for research purposes to answer our research questions. And some of the common methods that we already seen in our earlier introductions. Like you do surveys, you conduct interviews, you do observations, like I say, and these are all the qualitative methods, right? And we're going to, there's focus groups, experiments, secondary data analysis, then it starts going to the quantitative approach there. So these data are collected and then analyzed to either support or refute our research hypothesis. Remember, research hypothesis, there's no right or no wrong. If you already know it's going to be right, there's no need to do the research. Right? It's because you're going to do something that you don't know the answer to. That's why it's called hypothesis. The answer could be yes, could be no. It could even be proven to be a wrong hypothesis totally. Right? And then from there, we draw the conclusions about the particular problem that we were trying to investigate right from the beginning. And the importance of data analysis is to always ensure that the quality and accuracy, right? Quality of data we acquire, we gather, and accuracy of them. They should be error-free, and they must be relevant to the research questions. Later, we'll see more in detail about what it means by error-free. Is it possible to run experiments or make measurements without making any error at all? Or is there a certain error margin plus minus certain numbers that is acceptable? Right? And it must always the data that you go out to collect, whether it's a measurement, on-site measurement, on-site observation, whatsoever that is, it has got to be related to the research question. So do not, my dear students, be easily distracted and have your research pathway diverted to things that are irrelevant. Because the more you digress, the more detour you have to come back, right? The more U-turns you make. You keep doing that, it will be a very windy research journey. It will take a very, very long time. The shortest distance between 2 points is a straight line, right? So no matter how crooked the line may be, if you keep within a certain margin, you still reach the destination pretty quickly because it's still roughly a straight line. But if you make too many digressions and too many detours, pretty much like, a snaky path, winding over the place, then it's too long, right? What is the problem when we have too many distractions and doing too many detours? when the project is being prolonged, we are afraid that one, our motivation and confidence can be affected, right? Number two, we may run out of funds. If the project is being funded by scholarship or funded by a grant, there's always a limitation, due date to the project. And number three, we lose focus, all right? Our attention is really very short. Our attention span, our focus span for a project is also uh, um, we are stretching it. Basically, we are stretching it thin if we prolong or extend a project for too long. Right? So if we are in the master studies, try to go no more than 3 years. Right? No more than 3 years. If you are in the PhD studies, try to keep it within 4.5 years. Yeah. Anything shorter than that, well and good, well done. Right? But if you exceed, you go beyond that, maybe no more than 5 years for PhD. You go beyond it for masters, no more than 3.5 years. Yeah, you got to set some limits for yourself. All right. Always make sure that the data are relevant, valid, reliable, and reduce the possibility of having biases in that. And they are always representative of the sample that you examine. That's why you take average. That's why if you are trying to take the moisture content or soil sample, for instance, you don't take just one sample from the big bag of soil you have, right? You take 10, 21, because you're hoping that 10 or 20 small samples that you're taken up from that particular big box sample would be representative of what is in the big box sample. So if I only take two small bits from the big lump of soil, one answer give me 10%, the second answer give me 20%. Wow, what am I going to do? 10 plus 20 divided by 2? Or, no, I'm not sure now. I had better take another 10 samples. Oh, and from the 10, I can see if there are 10, 15, 11, 9, 8, 7, 6, then I know that the scatter is too big. The sample is too variable. Alright? So this is where I'm going to reliability. And it helps us to make informed decisions, and in your case, doing a research and leading to making a conclusions. To answer what? To answer your objectives, to address your problem statement. So that's why it is always very important to make sure that our data that we acquire will be collected using the correct method, analyzed using the suitable approach, substantiated, and then we are going to have form a solid foundation for making drawing conclusions for the findings there, right? And make sure that you circle back and answer your objectives, and that all this data is always supported for validity and reliability there. Okay. And when we look at our data, they can be simply divided into the primary and the secondary data. So primary data are the main data, the original data, the ones that we source it from the main source, the original source. Surveys, polls, interview, Delphi technique that you actually run a survey again and again among the same people, but improving it over time. Focus groups. Secondary data are things that information that we gather from, if you like, as a third party. Financial reports, sales reports, company reports, site investigation reports, vision statements, even internet resources. You notice you didn't get the data by yourself. You didn't do the measurement by yourself. You didn't conduct the interview yourself. You didn't sit at the site and collect that data yourself. No, you didn't. You read it from somebody else's report. So these are secondary. Simply put, the one that's not touched by your hand, seen by your own eye, heard with your own ears, then they are not primary data. Okay? And in terms of primary data collection, first-hand experience, I talked about it, never been used in the past, very accurate, very specific, because you are the one who did it. And the way we collect them could be done quantitatively, could be done qualitatively, right? I think you're getting the hang of things there. And to collect quantitative data, we can be doing a time series analysis based on timeline, could be doing a smoothing technique, meaning that find a pattern and find the best fit line there, or a barometric method. This is something that is quite exceptional. If you like, you can always explore more on that. Okay, we normally in engineering and together we are almost always in the time series in the smoothing techniques approach there. Okay, and quickly some the definitions here. If you can look at these time series, it looks like a plan, try to predict what's going to happen over a projected future time. smoothing technique, or a lot of data coming in, can I find a certain pattern there so that I can predict and estimate what's going to happen in future. All right. Barometric method is trying to speculate future trends based on the current developments, and they are based on events. So, looking at the bigger picture now, and these answers that you get actually serve as the indicators of what could be you plug in the system and see what's going to happen in future. If these parameters remain, or these parameters are being enhanced, or some of the parameters are being taken off the list. All right. Okay. What about secondary data collection? So these data have been used before. You are just reusing them. Okay, something that has been analyzed. You're analyzing the analysis, for example. So some of the information could be what some health and safety records, mission and vision statements, executive summaries, financial statements, lab results, survey finding. Can you see that, right? And it could be something that is from outside, external, government reports, press release, all right, archives from the newspapers, business journals, libraries, internet, plenty. So we always use data from these two sources without thinking, without pausing to think whether they are considered internal, external. It doesn't really matter. Just this is just for knowledge sake. Just so we know. Oh yeah, it could be from internal, it could be external. Then, all right. And the methods again could be quantitative and qualitative. The good thing about science data is that, as you already experienced this, I'm sure by now, when gone to your project, the research work, less time consuming and less expensive. Because readily by click or a few mouse clicks, and you can probably get off the database, or some it's an open journal is really there. For instance, meteorological data or some geographical um, uh, surveys of a place, you can go to Google Earth, and from the archive, they're all free. Yeah, you can easily acquire them, access and acquire them. Okay, right. So far, any questions? Is that all right? Please don't get stressed out. It's more like, as I say, it's not a sharing session. It's like, you don't have to memorize all these. I know tests, no exams after this, right? This is just, we are going to do a research anyway. You might as well know some technical jargons behind it. We are already going to do it, or we are already doing it anyway. So we try to put some names, right? Some names to what we are doing, what we've been doing, what we're going to do. And also some reminder to ourselves, including me, to make sure that we don't do it, we don't miss any points, we don't miss any steps, we do not sidestep unintentionally important components, right? And cost us dearly later on in our research work, especially when we are running a research towards acquiring a degree. Okay, let's take a look at model testing. It's a process where we try to evaluate the validity, all right, and the reliability of a theoretical model, which has been developed based on hypotheses, theories, or even prior research. Okay, obviously, you can see I developed this based on hypotheses, based on theories, based on prior research, meaning that it's pretty much on paper. Means that it is pretty much conceptual. It has not been proven yet by my real measurement, by my real experiments, right? We often use empirical data from the past, existing data, and to see if there's some kind of relationship there. And because there's some relationship, then that's why there's a model coming up. That is why I want to prove now with my own work that this small area where I'm going to examine will fit into this greater relationship. Right? With most of our engineering work has a similar, nice starting place. There are certain datum, there are certain baseline there where we are building our work based on the work of previous studies. Okay, and it is very critical, or in all areas, to explain and predict the outcomes. And you can see that what we're trying to do is that we try to fit the data into models. Is it a straight line, a linear relationship? Is it an exponential relationship? Or is there no relationship? Actually, it's all over the place, depending on the or which range of the data you're talking about, for example. Okay, so the whole point is that the next time around, someone is going to run similar tests, similar measurements. They do not have to run the full test, the full samples. They can then run the few, and they can fit the model and predict what's going to happen if they run the full set of the samples there. So you see how much of material saving, time saving, and labor saving that you are contributing. Okay, by just coming up with a model. And how do we validate this model? We test it previously. Now how do we validate it? Make sure it's correct. It's a process to make sure that do you write the logical arguments and something evidence that support the claim. You claim this is the right model. You claim this is a straight line. How do we know? It's a straight line. But I look at it, I think it's exponential line, you know. So it involves a very close scrutiny of the arguments and also the evidence that we have. Okay, just to make sure that the uncertainties or the variabilities are being kept to the minimum. There will always be, my dear students, there will always be a certain amount of uncertainty, a certain amount of variability in our data. No matter how carefully you run our experiments or collect our data or run our simulation, there will always be, because there's no such thing as perfection in the world. So there will always be. Well, the question is, how big an error margin am I prepared to accept? Right. So this could be something I determine myself with basis, or it could be something that's stipulated in the standard that I refer to. Okay, so try to identify that right from the beginning in your work. All right. One way we validate our model is by doing comparison with other people's work. That is called external validation. All right. You can be comparing with data from the literature, historical experiment data, and this involves what work that we commonly hear people doing experiments: calibration, sensitivity analysis, right? Signal analysis, false validation, right? And some pros coming up from validation testing. You can see that it all boils down to I'm more confident with my own model, and people are also more confident to want to use my model, right? For example, it ensures proper integration of the product or of the outcome into a desired or targeted environment. Make sense, right? So you want it to integrate and fit in nicely to a greater model, existing model. If it is not, my own confidence level towards my model is low. What about other people who are reading it and contemplating whether to use it or not? Even if I am the creator, I feel doubtful. What can I expect? What can I expect from the people out there in the industry, for instance, whom I expect to use my model? Yeah, that's why it's very important to have our testing or results validated there. Okay, now we go deeper into statistical tests and correlation study. Now, you see, time and again, we try to chip in about quantitative, qualitative. But primarily, we are still going to focus on the quantitative because most of our data coming through are actually quantitative, right? So quickly, data are like expressing quantity, amount, range, we know that's numbers. And the units will be there within with boundary limits like meters, centimeters, mm. It's a settlement of a building. What do I allow? Total settlement of 500 mil and 500 mm, and the differential settlement no more than 250 mm. For instance, what over how long? A year, 2 years, 5 years, depending on the site conditions and in compliance to the standard requirements as agreed upon during the contractual arrangement. And what are the arithmetic operations? Arithmetic, we are not even talking about calculus yet, right? Arithmetic plus minus multiply divide, like Ed Sheeran's album. So what are these operations applicable? Right? Simple stuff. And the difference I will try to see between these qualitative data compared to the qualitative ones are that numbers versus text or pictures, closed data versus open data, statistical versus various analytical approach, interviews, Delphi method, and generalization versus specific. You see that? You ponder a little bit, my dear students, see, true. If you are fully engineering based in your work, you see that you are very, very focused on the quantitative data collection and data analysis approach. Very seldom actually, very seldom pure engineering projects will dabble with qualitative. How often do you look at the picture or go to site, observe the worker and use that as your data input analysis? Very rarely, all right? Probably will be sitting as your traffic, for instance, your studies on traffic management, looking at the upgraded route, the safety, for instance, at the U-turn, how safe is the new U-turn, widening the road, and so on and so forth. So you probably have to sit down there, probably peak hour in the morning, 7 to 8, and then in the evening, 5 to 6, in between, which is 1 to 2 when the school are off, And within the more relaxed hours, probably like 9 to 10, and also in the afternoon, 2 to 3. So there are times that you actually go in to take measurements of the traffic conditions, for example. And what you're measuring is most probably the number of vehicles passing, the types, heavy vehicles, and heavy, what do you mean heavy? 5-ton lorry, 2-ton lorry, 1-ton lorry. Anything less than 1 ton, you consider a normal vehicle. You have no segregation between the two tired vehicles. You don't care whether it's a scooter, it's a super bike, what do you call that? Battery powered motorbike. As long as they're two wheel, you consider them to be all under the uh, uh, powered cycles. And then there are those manual cycles, for instance. So it really depends on how you specify, right? How you specify your data acquisition. So these numbers that you're going to take down on site in counting the traffic there is actually numbers. Can you see? But when you describe them, two cycle, battery powered or fuel powered or hybrid, these are descriptive. So already you can see the mix between quantitative and qualitative. Both the data they acquire for analysis is still quantitative. Yeah, I'm sure you can see the difference there now. Again, further looking into the difference between quantitative and qualitative. Quantitative data may be instruments like measurements with rulers, balances, graduated cylinders, beakers, meters. Basically measurables. That's why I come with numbers. Qualitative is more words, more descriptive. It's something I observe using all my senses. It could be something I hear, I listen to, something I see, I watch, I observe, something that I taste. Now, for those who are in the hot cab or in the culinary area, could be doing that. All right. And the types of data, if this would be a lot more easier to grasp. If I'm talking about quantitative, and talking about scores on exam, my ranking, what are the weight, the height, the shoe size. Qualitative, I want people's names, and from there I determine their ethnicity. I associate with the ethnicity, or is it associated with their religion, for instance? What about the smell? Aromatic, buttery, pungent, acidic, or the colors. You see, very different, totally different. Okay. Now, this is where it gets very interesting, where qualitative and qualitative data becoming a bit blurred, the line is blurred, but it still doesn't change the fact that you are doing a quantitative approach or qualitative approach, right? So let's take a look at this. If, for instance, we're talking about computer now, just a computer situation. I'm doing a quantitative research, all right? So being objectively asking the question, the answer would be, yes, my chip speed is 2 gigahertz. But if the question is being framed in a qualitative way, you'll probably be asking, do you have a computer? Is it? And the answer will be, yes, I have. No, I don't. Right? So this is being qualitative. But it's still an objective question, right? The answer is yes or no. It is not an open-ended question. I can answer, my computer is plain. I like it to be circular. I don't like an 18-inch. I like a flat screen. Irrelevant. Is it? I still limit. I still make the answer very objective. That is a yes or no. But if it's in a quantitative manner, yes or no is not good enough for me. It's too descriptive. I want numbers now, right? You have one, right? So tell me the speed of the computer, for instance. What about if I turn it subjective now? In a quantitative manner, now, the statement could be, on a scale of 1 to 10, my computer scores 7 in terms of ease of use. Ease of use is very subjective, right? To me, this laptop is Asus, I don't know what model, is suitable for me. I find ergonomic, I find comfortable, I like it. Even the screen glare is just nice for me, all right? But another person may say, wow, this keyboard is super hard. It makes too much of a cracking sound when I type it, so I'll give it a score of 4. You see, it's very subjective now on the same thing, right? But if it's a qualitative way of looking at data and allowing subjectivity into it, look at the answer. I think computers are too expensive. See? When things get qualitative, it is very open to interpretation. Very open to interpretation. But when things are quantitative, there are numbers coming out where if I ask 10 times the same question to 10 different people, 10 samples meaning, I will get answers in terms of numbers, which I can further analyze using statistic approach and so on and so forth, right? Regression and so on and so forth. But for qualitative approach, it gets a bit tricky. Well, at least for me, I'm from an engineering background, so I think it's tricky. So I would say yes, no. Someone would say it's expensive, moderately expensive, affordable. I can't afford it. These answers, how do I range them? How do I quantify it? Okay. So now let's take a look at discrete versus continuous. Data coming through could be quantitative data now, numbers, could be discrete, countable, final, individual, one by one, or could be continuous. So continuous, I said engineering wise, we are almost always on a time series though. So infinite could be a flow, for instance. So take a look at this chart here. This is just a temperature record over a week. On the y-axis, is actually the days in the week, Monday, Tuesday, right to Sunday, and on the x-axis, the temperature. Looking at the fluctuations here, you can see that this place is of a temperate zone. Whereas in Malaysia, it's unlikely that you're going to get 10 centigrade. Now, with a cloudy day like this, you probably still hover around 30, 32. Okay, a super hot day in the early parts of the year, then you probably have things like touching 38, 40. Yeah, you can really feel the heat then. All right. So in terms of continuous data, you can see that the infinite values would be looking at the data across the week. So if I were to plot this, the peak of each bar chart here, I will find a trend and it becomes a continuous data for me. Or if I just want to know discretely Monday what is the temperature, then the bar is good enough. I don't have to plot in the lines there. It really depends. The same set of data, same information here. Depends on whether you want to look at it in a discrete manner. Maybe you want to talk specifically about Monday. Maybe Monday was a special day where there was, for instance, reported to be a what do you call those events? Eclipse. Yeah, an eclipse going on. So how does that actually affect the temperature on that particular day within the 24 hours? Maybe you go plus 10 hours and minus 10 hours before and after that eclipse. So then you'll probably be looking at Monday and Sunday before, and also Tuesday after that. Things like that. Okay, so that's where you have to see specifically the discrete data for the particular time. But if you are interested in a trend within a span of time, then it is a continuous pattern they are looking at. And there are situations there where you can actually change the qualitative data into the quantitative one. For example, I actually rank students' performance poor, fair, or excellent. So when I've taken off, I measured, I collect the data from students from their test results, for instance. And I say, okay, out of these results, I'll say that if you score between the 0 to 30, you're considered poor. From 31 to 70, you're considered fair. Anything beyond the 71, they're considered excellent. Then now there are numbers coming through. Even though originally it was qualitative. And see that? Yeah, because now I am capturing the information on what the number of students who fall into the range. The range poor, fair, and excellent are originally qualitative. You see that? Okay. And another example is that how many males and female students there are in this group, in this sample, in the population. So there you go. You turn something qualitative into quantitative. What about the other way around? Can I turn a qualitative data into a quantitative one? Take a look at this. Data could be qualitative, quantitative. We already learned that. And analysis, again, it could be a quantitative approach. It could be a qualitative approach. If my data is quantitative, let's take a look at this. Let's follow the sequence here. If my data is qualitative, all right, and my analysis is also qualitative, I'll be trying to do what? At the beginning, at the outset of my project, I'll be trying to look at the context and the goals, the big picture. Right, the big picture. So that would be qualitative data versus qualitative data analysis approach. And then I start to identify, to determine what are the kind of suitable questions to ask. All right, what are the suitable statements to be put in my survey form, for instance, a questionnaire that is qualitative because of statements, descriptions, or I'm trying to run a quantitative analysis after this, because when the data come through, I'm going to put them into range. I'm going to put them into numbers. I'm going to hit the average, average of how many people will actually say this, or how many people will be on the down saying, commenting negatively about something, how many will be commenting positive, how many people will be in the normal zone. So you have the normal distribution there, for example. So I turn something, data that is qualitative into a quantitative outcome by applying the quantitative method. You can see the pattern there? Yeah. And what about quantitative data being looked at in a qualitative manner? Statistics, mathematical analysis of the results, right? I got the results, numbers now coming out from the graphs and all. Results come out, I describe them. Why is the graph going up and then coming down? I explain them. These are words, these are texts. So these are becoming descriptive, these are becoming qualitative now. See, the analysis is qualitative. Last but not least, we go up the meaning. I want to draw conclusions now from my findings. I want to give meaning to them. I want to circle back to my objectives and answer those questions that I posted to myself right at the beginning. Now my data is quantitative, but my approach is qualitative. I come up with words to describe them. And see that? All right. So you see, even though in the engineering arena, we do this. It is switching from between data and analysis approach, qualitative, quantitative, quantitative, qualitative, and they are mix matching all the time. So depending on what are we looking for. So there's no need to frame ideas, there's no need to memorize it, there's no need to. We do this all the time. It's that it's good to know that that is what exactly we are doing. Right? The different contexts, different projects, different coverage, different parameters, different measurements, different data, different research nature and all. But the process is very, very similar. Right? Just like what we mentioned just now, the data is quantitative. But if I execute it, the analysis in a quantitative manner, then I come up with more numbers to more numbers. Temperature throughout the whole week, right? 7 days, 7 data into one data into the average. Quantitative to quantitative again, right? For example, the terms that we use. Again, obviously, the quantitative ones, numbers, units, qualitative, adjectives, if you like, easy, I like, it's awkward, squirrel. Maybe it's a question of who is ruining the crops more. Is it the squirrel? Is it the rat? Or is it the raccoon? Or what? For example, it's something, a few energy consumption. Is it efficient? Moderately efficient? Badly efficient, for example. Okay? Okie dokie. Now we go into the analytical procedure. See that we zoom into the quantitative approach, testing on the existing theory with deductive approach, which is like Sherlock Holmes or an investigator, police work, if you like, try to deduce what is going to happen. I have a theory, I have a hypothesis, and I'm going to test it whether it's right or wrong. No, sorry, I shouldn't say right or wrong. Whether what I think could be, would be. All right? So it's doing deductive there. The deductive work there. So let's take a look. Whereas qualitative is going to down the inductive pathway, where you develop a new theory from there. See, very different, yeah? One is almost like what you say, reverse engineering. One is going to talking about coming up with the new theory, new way of explaining a situation. All right? Okay. I hope this little cartoon here would be easier for us to grasp how to run a quantitative analysis. There's 3 stages and 6 steps. So when we talk about the stages, then we are talking about, start off with the first stage of problem identification and also reviewing past finding. There's a problem, I frame the problem, this is a problem that examine. How do I know this is a problem? Surely I must be referring to other people's work to prove that this is a problem. It has not been resolved. There's a gap. I need to fill it. You see? The sheer review. Then I move on to solve the problem. To solve this problem, there are 3 steps. First, I need to do some modeling. Remember we talked about that? How would the model, what kind of equations we're going to use here? Which equation or which principle is going to be applicable here? Is it 1? Is it 2? Do I need to crisscross between the several models there? And then I go and capture my data. Go and do the measurement. Go and run the experiments. Get the data in. Now I look at my data, analyze them, whether it's quantitative or qualitative, in what? In comparison with my model. Remember that? We just say that these days in engineering world, if we could, we simulate first so that we can predict what's going to happen and we try to avoid all the pitfalls before we actually run ourselves into it. All right. And last but not least, obviously, the last stage, last step is to conclude and to present our work. What's the good? What's the good of doing a research if we can't share our result with outside people? We can't present our work. Only we can understand the figures, and then nobody else will understand that. We draw a graph, only we understand, elsewhere don't understand, and nobody else is interested to look at it because to them it's irrelevant, for instance. We don't want that to happen. That's why, my dear students, it's very, very important, all right, to set it down in your research methodology in the early days of your research. But do not fret, don't be upset if you think your research methodology, the GPS is not quite I wouldn't want to use the word certain, but not quite solid yet. All right, it's okay. Year one, sem one, no one is expected to be that solid, that firm with their theoretical framework yet, or their what do you call that? The research framework yet. It is something that is very ironic actually. A research framework, the name framework gives us the idea of scaffold. A scaffold is a skeleton. It has got to be solid, right? As solid as can be. Nonetheless, just like our human skeleton, solid as it is, to keep us upright, it is also flexible. So we must always be prepared to be adapting to the changes that come along the way. I'm not talking about changing the objectives totally. I'm talking about tweaking the objectives eventually. When you come to your findings, we will see when you get there. But what I'm trying to say is that nothing is carved in stone. Nothing. Nothing is fixed and certain 100% in our research work until the very day we put the full stop, the last full stop to our thesis and say, that's it, I'm going to submit for Viva. And even that, there'll be the Viva, there'll be the amazing discourse of your life for 3 hours perhaps, and then you do some simple corrections and that's it. That's it, the final full stop. So even then, because you have grown so much more mature and you have known so much more since you started your work, you have ideas. You probably will refute yourself in your own thesis. So that is a fun thing about doing research. Okay. And just another example in a picture format to show how we actually run our quantitative data analysis. We start by looking at what are the requirements, you set the ground rules if you like. What are the parameters, what are the source and scope, what are the limitations, where what samples will be collected. Am I going to focus on the Johor contractors, for instance, or go southern zone, which goes a little bit up to Muar, for instance, southern part of Malacca, and so on and so forth. Or I go up to southern central zone, for instance. So it's really up to you, for instance. And then the analytical approach, what the analysis is going to run. All right. Going to then how do I design my project here? I'm going to do which lab? Is it this lab in the campus or the lab that I need to, some samples need to be sent out to a commercial lab because you don't have the equipment, or I need to borrow the lab from other universities. And then I set up my test, whether it's a model, whether it's simulation, whether it's a setup on site, whether it's in situ measurement, anything goes. And then I run my testing, gather the information, and finally, I got the findings. I share it out. I deploy the summary. Okay? Yes. This is a fun day. My dear students, sometimes we begin setting our GPS and we thought that we are going to Malacca. All right, this is Johor, going to Malacca, going up north. End up, you see, where is the Merlion in my side view mirror? Oh, I end up in Singapore. I'm supposed to go north, instead I go south. Oh, that's an extreme case. What I'm trying to say here is that sometimes we think we are on the right path. Sometimes we are so certain, so confident that we are going the right way, but actually we are going in the totally opposite direction. Is it wrong? No, it's not wrong. It's just that it's not taking us where we wanted to be. That's all. All right? So be a bit cautious about it. So here we go. We may begin something qualitatively and we end up quantitatively. Let's take a look. It's like a bull's eye, like people who do archery. Qualitative research without quantitative elements, you could be hitting very close to the bullseye, just not quite the bullseye. If you're doing it quantitatively without any qualitative element, we could be hitting a certain zone, always the same zone. So we thought we are right, but actually we are not quite correct. So let's take a look at what does it mean. If I run my work qualitatively without any quantification, without any quantitative elements, I could be asking the right questions, but don't get enough data to correctly, accurately answer the question. For example, uh, fishes in the river are dead. I wake up one morning, the river, all the fish are dead. Okay, so I got to ask people in the villages around there, what do you do? Do you dump poison in there? What do you do? Do you blow up the fish? Do you throw some poison in the river? What was so you asking questions? So the question will come true. But because you're only asking the villagers, the answers are only limited to this population. So you are not going to get the correct answer. Maybe some villagers will tell you that, yeah, I saw someone playing with some poisons. I saw someone bringing some drums or liquid out there last night. I'm not sure. I think it's there. I'm not sure. Someone say, I smell something. Or someone say, I saw a truck leaving, an unfamiliar number plate. It's just, it's almost like a hearsay. But I'm still the correct question. What happened? What happened to the river? What happened to the fish? I'm asking the correct question, but not quite getting enough data because I'm not quite addressing the adequate samples there. So we may be hitting the bullseye, but we don't know whether or not it is a fluke. It so happened that every time I ask the question, I get the answer is there. Everything is pointing towards somebody dumped something there. You get what I mean? Same thing, same point, but it's just not quite the bullseye. Or I'm using a quantitative approach. I may be accurately answering the question, but maybe it's the wrong question to start with. It's like using the wrong tool to do a certain measurement. Of course, the answer is correct, but the tool is wrong. Extreme case. I want to measure the weight of my mouse, and I use a ruler. No matter how many measurements I make, however correctly I use my ruler, however correctly the measurements are being made, including the curves and all, it is not the right answer, right? Because the question was, what is the weight of the mouse? All right. So it's again going back to the river where the fish all died. So I could be asking I could be measuring. All right, now I come in, I'm more scientific now. I come in with a tool, device. I'm going to check the pH. I'm going to check the pH of water. I'm very certain it's poison. So I check the pH at every point. Every 100 meters, I check the pH. Every depth, I check the pH. So I get a lot of data there, right? Scattered over the place, but it's all in a certain zone. It's all the pH. But then, how do I know? It's because of the pH that the fish died. What caused the pH to be falling in that zone? Poison. How do I know it has poison? So we can be so confident we are hitting in a certain area and we may think it is the bullseye when it is so far from the bullseye. Just because they repeatably, no, that the data we got is so repeatable. So in the same place, we thought we are correct. But it's not anywhere near the bullseye. And see that? There could be a situation like that. We are measuring a parameter that's irrelevant. The pH has got nothing to do with the toxin. Or the fish didn't die because of any changes in the water. It was because of the temperature. Or it could be because they were electrocuted. Somebody dropped by accident a generator into the river yesterday at a certain hour and the fish died. You see that? So investigative work, doing qualitative without quantitative, doing quantitative without qualitative. So we end up coming up with results that are can be very misleading. So be cautious about that. So the summary of it is there to say that if we do quantification without qualification, remember both sides situation, scattered, the second example, then it could be irrelevant, asking the wrong question, getting loads of data, correct answer to my question, but the question is the wrong question, right? Or qualification without quantification, leading to inaccuracy. Asking the right question, but I can't quantify it. Why did the fish die? 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 Yeah, it's a correct question, but all sorts of answers are coming in. How am I going to quantify that? See that? Like there's an interesting food for thought there. You can just go through this again if you like. Okay? Okay. Is there any questions so far? All right. Okay. Well, if you need a break, please just take a break yourself. Go make a cup of coffee or whatsoever. You need to use the loo. Please go. All right. This is recorded anyway, so I believe that you can always go back to it if it's necessary. Okay. Okay, I just press on then. Before I lose my voice. So yeah. So the data presentation. This is interesting because as engineering students, we especially like when we see the data coming out. Right? We don't much like when we are collecting the data. It can be so painful. I have to stay 24/7 in the lab. I need to be in the on site 24 hours. It's so hot. In night, it's so cold, for instance. So it's so painful. It's hard work. Right? But when the data is in, I just sit in front of my computer with the aircon on, with cups of Zeus coffee ready for me, and all the pastries, sweet cakes, and all. I just keep, I don't know, clicking my mouse and pressing the on my keyboard and get the data running. And I see the graph coming. I'm so happy. The sense of gratification. Yeah. So we like that. However, my dear students, remember, because those data that come out from our analysis, whether it's a graph, whether it is a table, they are going to present, or rather represent what we have gathered from the lab, from the experiments, from the site, from the population, from wherever there is we got the data. It has got to be telling the correct story. It has got to be able to represent what was measured, what was interviewed, what was surveyed, what was gathered, and so on and so forth. That is why representing the data. Okay? As I say, our data analysis must be representative. Representative of what we measured, what we observed. Otherwise, there's no data presentation. It's just data for show. It's meaningless. Okay? Make sure that our data presentation is, number one, contextually grounded. Contextually grounded. If I say I want to measure the weight, then I use a scale. I measure the weight. I do not use a ruler or a thermometer. All right? Theoretically correct. Remember, we're starting out, when we said though, we must know what is the grounding theory or the underlying principles. Heat mass transfer. If I were in geotechnics, I'm going to look at the slope failure, for instance, or induced by rainfall. So what theory am I looking at? Am I going into the unsaturated soil model or what? So you got to know that. You got to set that as a baseline. All right. And how does it contribute? All right. Is it or rather, is my work of any meaning? Is my work of any significance? We almost always like to round out our chapter 1 by saying the significance of study. And we just write it because everybody seems to have significance of study in their chapter 1. Have we ever paused and asked ourselves, what is the meaning of significance of a study? To have something, a piece of work considered significant, meaningful, impactful, it has got to be making some contribution, right? No matter how small. No matter how small. To the existing body of knowledge, to the practice, to the industry, to a certain database, to a certain work process, to a certain way of doing things. You see that? A certain contribution. Then when we talk about impact, significance, and so on and so forth. Understand saying? Yeah. Hence, it is always good, yeah, with your guide or your supervisor, with the assistance of the supervisor, to have someone from outside, academic, non-academic, engineering field. Usually, you can get the practitioners, engineers to review your project proposal. All right. And to do a project that is sponsored by a grant, funded with a grant, is a good typical example of a project that has been reviewed by the professionals, because a grant is only given, awarded, because the grant proposal has been read and reviewed and examined. Your supervisor may even have been interviewed by the panelists. So it has been examined and endorsed as valid in terms of worth to be examined. Hence, you are the researcher, the student coming in to run the work. Can you see that? So that is one example. But if a project is brought in by you, or brought by the industry, or an idea by a supervisor, it is good practice to have it checked right from the beginning, reviewed by a third party, if you like. One good example that your faculty, your respective faculty, is helping you doing this is the proposal defense. So my dear students, bear in mind, try your very best to have your proposal defense done no later than your second semester. I understand some of you are working, so it may work commitment and so on and so forth. You may have to drag it to the third semester, but if you could, have it done within the first year of your study, so that your GPS setting can be fine-tuned and you can get going. Because until your proposal is being endorsed, until your proposal is firm, it is very hard for us to be running our project in a confident manner. Understand that? Okay. Now, reporting data, it's important to keep in mind that whatever we present there should be self-explicable, meaning that you just look at your table or your graph, I can understand what's going on. Of course, I must be from the same field of study as you, right? Nobody will read our thesis unless they are of the same area of research. Trust me, I'm from geotech. I wouldn't be reading someone's thesis who is looking at I don't know how to grow paddy, for instance, and vice versa. Because we're of totally different area, and I wouldn't understand a word in there, right? So, and I wouldn't be able to appreciate the value of the research there, all right? So same thing here. To make sure that whatever we present there, the graphs or tables, are self-explanatory. Without having to look at the text that you put down your thesis to explain the table, explain the figure, I'll be able to explain to myself what's going on, all right? And hence, it's important to put in information like sample size where necessary, where applicable. If it's just a list, a table showing that sample A, B, C, D, E, or your sample name itself is indicating the content, for instance, sample 1%, 2%, so it's not applicable, that's all right. Or if it's a lot of data, and these are like you have hundreds of samples, when you have say for instance you have 100 samples, and you group every 10 of them into groups. There's a group A, B, C, D, E. So there are 5 groups of 20 each, for example. So your answers will be, so for each group, you take out the average of 5 samples. So maybe E1, so A1, A2, A3, A4, A5. So people will know that A1, 2, 3, 4, 5 from every group B, C, D, E, they are all representing the 5 average, the best average from that particular 10 or 20 samples in that particular group. So that is why it's important, right, to have all this information written down in your table or on the slide of your graphs. So let's take a quick look at this. I hope this will take away your drowsiness if you have not already fallen asleep there. As examples, take a look at this table, my dear student. Is there anything wrong with it? Can anyone tell me? What do you see, and what would you like to comment about this table? Or you like it? You think this is a good table? Or no, there's something that you don't like? Anything? Anyone? Don't bother about the data, really. This is about sales figure, right? We are really looking at the presentation of the table. Is there anything you would like to comment about it? It's not organized. Yes, it's disorganized, right? And a kind of messy. Yeah, out of alignment and not good. Now, let's be specific now. Misaligned. Yeah, bad. Sometimes it's bold. And then the others are not bold. They are misaligned. And this is an S coming off, not aligned. And numbers are all without decimal place. Suddenly, in the average, there are decimal place, and there are a lot bigger font size. So this is a bad table. Do not have this in your presentation. When I say presentation, it could be your thesis, could be your technical paper, could be your PowerPoint presentation. All right. Now take a look at this. The same data. When you put it in a format that is organized, several things become immediately clear. One, the names are arranged by alphabetical order. Okay, so it's a lot easier to find. The average is being bold. No other things are being bold here, because my key thing about this table is to tell people the average achievement or average sales of the respective persons. Whether it's then the items, widgets, gadgets, doohickeys, I don't know what that is, to be honest with you. The numbers are put in, and I can read up for berry block, for instance, widgets 180, gadgets 165, the doohickeys 156. You can see that clearly. All right. And the fact that the average is done according to the column, the type, the category, meaning what? Meaning because the sales figure, it is not important who does it. It's only important to the company. And for each item, what is the average hit? You see that? It's not about you. Berry block, what is the average sales? It's irrelevant. Get it? So same thing here in your own research work. You got to present your data in a coherent organized manner so that it's immediately understandable, decipherable by your readers. It don't make your examiner have a migraine trying to read your tables or your graphs, because your first reader, your first official reader, the first official reader of thesis is your examiner. I don't count the supervisor. It's the supervisor's job to read or review your thesis. All right. For the first person to really read your thesis for the first time and to examine it is your examiner. So do not make it a nightmare for the examiner. All right. A second example. Take a look at this now. Well, what is wrong with it? This is about in the maternity ward. The data coming out from the moms going in to deliver their babies. So, what do you see in general? Is there a problem here? Or you like this table? Hmm? Any comments on this particular table? Do you like the title? It's a 4-line title. Anything? Yeah, the title is super long. I finished the third line. I forgotten what it said in the first line. Oh, that is no good. Okay, no fewer than 31 words. Out of these 39 words can actually be deleted. Right? It's just details of 80 diagnostic cases of first trimester chorionic biopsy. So be careful, yeah, because I think these days is a lot easier. You have AI to help you ask, have the title, ask ChatGPT to give you a title there. That's not plagiarism, okay? It's your own thing. Feed your own information there and ask for a nice title there. So don't try to give something that's a whole paragraph and no one can read that and try to comprehend. Okay, now another example. If you take a look at this, you compare this table one and table two, top and bottom one. Same data here. So you can see the pattern here. Rearrange the vertical order. All right. This is about logging. All right. Logging information over the years and the numbers are being put in. If you're already talking in thousands of tons, decimal place is meaningless, right? Yeah, you don't need the accuracy anymore because you're talking about thousands of tons. So just round them up and you can see the years, the numbers coming for each place, the average of each site, paradise, Millstream, and so on and so forth. And then finally, average down for every year as well. So you have average per location. You can also average per year. So this is a good way of summarizing your data. All right. Depending on what you want to show. Okay. Now let's take a look at graphs. Is there anything you want to comment about this graph? Don't bother about the data, just a graph that contains two sets of data, right eye, left eye, and some symbols used, some lines used. Do you think that it is being excessive? Do you think there's something that you don't quite like about this particular plot here? Anything? No, you like it? Would you plot your graph like this? Anyone? Yeah, anyone? Do you want to comment about this graph? Oh, that's pyramid. They're just showing that with the pupil diameter going up, the tyramine, a certain chemical that they use for induction of this tag is going down. That is not important, that is content, sorry. It's the graph itself. Um, right eye, left eye. The way they plot they use the symbols, the way they use the lines. Is there something you want to comment about that? No? Happy with it? Do you not think that it is a bit too uh, overdoing it in that I want to show the difference between right and left eye. I change the symbols and I also change the line when maybe just doing either will do. If I want to change the symbols, one is a full circle, one is a open circle, then the lines do not change, right? I can readily identify the filled circle is the right eye and the blank circle is the left eye. Or I just want to show, actually emphasize on the trend. Is what time. Remember, in the time series, the points are irrelevant. I just remove the symbols. I just show the lines. So apparently, in the about an hour, 60 minutes, the pupil dilation is the greatest, and then it will actually go down after that. So 60 minutes is when both eyes will start to react the most. And see that, for example. So what I'm trying to see is that don't overdo the graphs. All right. If you are to change the symbols, you don't change the symbols and then change the line type. Line from dash line to dash dot to dash dot dot dash, So there's no need to overdo things, but while Excel give you the options, use it sensibly, right? Use the option sensibly there. Okay, so much for that. We move on, almost coming to the final part of our sharing this afternoon now, on the data analysis and interpretation. Okay, let me have a look. Almost there. So when we are analyzing our quantitative data, essentially there are three steps. First, we validate. Next, we edit. And three, we code it. All right. So wow, these terms sound so, yeah, don't worry about it, just some terms. So first step, we validate. What is the purpose of doing data validation? It is actually to identify as best as we could whether our data collection method, our measurements, our experiments have been done per the standards, per the prescribed method, without any bias, without any error, intentionally or unintentionally. Okay, if I follow it according to British standard or ASTM or whatever that is, I have follow right to the dot. I cross all my T's, I dot all my I's, and if there's still error, it's experimental error now. And not because I skip a step or I mixed up the steps of things are. And in the doing data validation here, we have 4 steps: fraud, screening, procedure, completeness. Let's take a look. It's very interesting. Fraud, as the name implies, this is scammers and all. In first, whether each respondent was actually interviewed or not. This is in the case of if we are interviewing. If you are doing a qualitative approach interview, you say you want to interview your population is 50, you interview all 50, really? You interview 48, 2 were missing. You simply pull 2 from another population. Oh, that is not quite correct. Okay, there's a fraud data there, for instance. Screening. Chosen them per my research criteria. I just say that I only want to interview, for example, collect data from the feedback from contractors, class B from Johor. Okay, and then suddenly there are, I'm supposed to interview 30 people. There are 10 who are from Selangor, Malacca, and Penang. That is poor screening. Procedure. Check whether my data collection procedure was duly followed. I already say that I have 10 questions to be asked. They must be asked sequentially. 1, 2, 3, 4, 5. I do not mix up because that will be leading the interviewee to answer my question if I skip the question of this side. But I do that. So that is not procedure enough. Last but not least, completeness. And make sure that I ask all the questions and not just the few. I skip. For the first 10 respondents, I ask question 1, 2, 3, 4, 5, I do 10. The next 20, I'm so tired, I ask 8 questions. By the time I come to the 100 respondent, I only ask 1 question. That cannot be. So you see, qualitative research, my dear engineering students, it is very painful. It can be very tedious and painful. So do not simply jump into it if you don't know. Okay? Always make sure that we consult the experts on how to do it correctly. Like in this case, if you are doing this is an example of quantitative data validation for a qualitative research. Be very careful. Before even you got any data in, just going out to collect the data, already you need to do some validation. Otherwise, there's no way you can quantify them correctly later on. All right? Next, how do we edit our data? When we say to edit our data, I don't mean to manipulate our data. It doesn't mean that you don't have data, you create them. This is where we have got the data. Of course, we churn out loads and loads of data, rows and rows, columns and columns of them. A lot of times, engineering-wise, data either we manually chart them per time or per a certain criterion. Otherwise, we have a logger. There's a stencil being put down there. It's measuring some distance displacement. You probably use an LVDTs. You are measuring the stress or load transfer mechanism over time. You have a pressure cell or you have a load cell down there. And all these will be connected to a data logger to log the data for you as frequently as you like. 10 per minute, 10,000 per minute, depending on how precise, how fine you want your data collection to be. so that the data logger is connected to your computer, some software, and some even run the analysis for you. Or if the most basic of all, they will actually gather data out and allow you to extract and export the data out in a readable format, like in .xls in a Excel format, so you can copy paste them into your Excel spreadsheet and start analyzing them to turn out tables, graphs, and so on and so forth, regressions, and so on and so forth. You see that? Yeah. So this is where we see the raw data. What do we do? Because typically, when the larger your data set is, then the errors are there. All right, the errors will be there. So when that happens, we are going to have to run a quick data check to identify outliers and the missing data. So what is this? Let's take a look at the example. It's easier. Outlier. Outlier is something that is so different. Like a penguin. You have penguins lined up in a row. Black, white, black, white. Suddenly there's a pink. Wow. So definitely that's going to stand out, right? That's the outlier. And to detect this outlier can be a very subjective exercise. Right? You see pink, but actually it's not really pink. It's dark pink. So dark pink, and it looks a bit blackish pink, so it's still black. But I think it's pink. You know, the other person says it's maroon, so it's very subjective. So for instance, in a very quantitative manner, that kind of ambiguity would not arise. Look at this amount of money that we picked up for 12 days. Numbers, suddenly there's day for wow, there's 101. Other days you have barely 10 bucks. The highest you ever got was the 9 ringgit. All right. So this must be odd. So something is wrong here. Either it's true, it's real, or it's a typo. Actually, it's 10.12 or 10.1. It was a fat fingers typing incorrectly on my calculator or my keyboard or things like that. See? Very obvious outliers. Different for other people. Or in the graph, everybody is in a range, right? Within no more than 10, and then suddenly you have one that's here. Do that? The same data from the previous table now put in the histogram format. And see, you can detect that very quickly. So it's like visualizing the data and see the outlier. And again, an example of graphs, plotting graphs are good. This is a graph that you can see. You could probably question me, where are the labels? What is this y-axis? What is the axis? What I'm trying to say is that this is the kind of graph you should be plotting for yourself when you extract the data from the logger immediately. Say my data runs for 24 hours and every hourly I can actually extract the data. It's real time. I would put it in Excel and plot the graph without bothering to put y-axis, x-axis. I already know what y and x are actually. I just want to see that the pattern is there. So once I plot it out, I expect it to be flat line. For instance, for the first hour, I don't expect a lot of fluctuation. It shouldn't be fluctuating more than 20, for instance. So I can see here, yeah, that's all right. Yeah, correct. So within maybe the first 12 hours, yeah, it's roughly there. And then there's one weird one here. Sorry. There's one that is gone to 100 here. What happened there? Then I see if this is the fourth hour, for instance, I can go back and check in my logger and something spiked there. Is it a temperature or someone knocked at the desk and my equipment has been shaken or what? Or sometimes it's just a fluke. Then when I average my data, this has to be taken out. Otherwise, that's going to affect you, right? You take all these and you divide by, say, that 10 data points, including these. If you're going to divide everybody, including the 100, the answer is going to be very different from omitting these and divide everybody by 9. Can you see that? That's why outliers, it is very important to identify and to put them aside when necessary. I don't need to erase them from the graph. I need to circle them out and inform in your thesis, in your description, that there is one odd one there. Either you can explain it or you cannot explain it. It's all right. But when you do further analysis, right, running analysis, average, and so on, you got to make sure that that is not being included. All right. And next is, that is easy. Oh, you can see it's so off. It's 100 off. The others are less than 10 on the graph. How do I actually detect outlier? The simplest approach we all learn in our lower secondary statistical method. We sort them out, small to large, low to high, and then try to sort and filter and see the odd ones out. We do them the quartiles, and we know we do these those things. For example, is normal distribution stuff. All right, so you find the quartiles where they are. So the weird one is lying out there, and you can see very obviously inner and outer fences, upper lower boundaries. So you can explore these if your data is a lot and a lot. So you need some statistical tools to help you there now. Okay. And what about missing data? Those are outliers. But what about missing? Yeah, we are humans. We are only human. To err is human. So we tend to make mistakes. We overlook. We are counting the traffic and then we miss that particular one. It's like it passed. I just slip my mind after 1 hour under the hot sun. I can't concentrate anymore. I missed that one, the police pass. I saw that it's pink, but I can't remember whether it was a truck or whether it was a car. Right? So what do I do? And similar in this case, um, what do I do? Example here, I have names of people, I have the age, I have the gender. And then when I've forgotten, I wrote down Jamie and then, hi Jamie, hi, bye, bye. You can go and see a doctor now. I've forgotten. After one day, I've forgotten whether it's a male or female. At that time, I was pretty certain. But now looking back, Jamie could be a boy, could be a girl. Am I right? Similarly, item number 7, entry number 7. I wrote down it's a male, 35 years old. Maybe someone I knew from my neighborhood. I was chatting, and then I forgot to write the name. And now after a day's hard work, I've forgotten. I can't recall. So in my corrected data set, perhaps I need to omit them now because I don't know. I can't go back and do it again, right? So I got to omit. So instead of having 1, 2, 3, 4, 5, 6, 6 data sets, now I have remaining 4. So it goes on to show two things, my dear students. One, this is a listwise deletion method. If it's not there, I can't recall. There's no way I can go back and retrieve the data. I have to delete it. I have to delete, right? Two, it is very important. We have 100% concentration and focus when we are gathering data out there, especially information that we cannot go back and retrieve again. If you've got a logger, well and good, you can go back and retrieve the data. If there's no logger, you are using a dial gauge, manually reading the data. Past means past. You can't go back, what was it 1 minute ago? We can't. That is why it is very important, yeah, my dear students, to have your 100% heart and soul and mind when you go to the lab, when you go to the site, when you are out there collecting the data. Especially if it is a very, very crucial primary data. All right? Remember that. No one says research is easy, right? Research is fun. Um, Research is meticulous. It teaches us to be cautious and pay attention to the details. And it's always the details that bring you the success of your work. And again, how to deal with missing data? The second approach, the second strategy or second method is the LOCF, last observation carried forward. Oh, forget about this statement. I don't think you can digest this anymore. Let's take another example. Names, and I measure and record their weights over time, right? And I have Robin, I have Heather, I have Jamie, and I find that, oh, there are times that I have Robin didn't show up, so I didn't have the data. Similarly, Heather didn't show up in May, June, and also January. I don't have the ones for Jamie, January, and in the April and May as well. So I don't have. So what do? If I use the last observation carry forward approach, I just fill in the blanks using data from the previous record. It was 68 in February, so I presume it didn't change in March and April, so it's still 68 instead. It's not accurate, it's not necessarily true because I can't go back and measure anymore. Time has passed, but I just fill it up with the previous data. Can you see that? So this is why we're doing it. On condition, we have of course the subsequent data. If you look at Robin, while I do not know what exactly the real data for March and April, I do have May. So from February, it was 68. I can see the pattern here. January 65, February 3 kg increment to 68. By the time it comes to May, it was 72. So the likelihood that it has become 69, 70 is pretty high in April and in March and April. But because I don't know, I don't want to speculate. I just take what was before and I note down, right? I will note down in my spreadsheet that these were taken from the last observed information here. So when I plot out the regression, it's plot the time series, it will still look odd, and I'll still note down that these 2 points were actually taken from the previous data. Okay, as well we are doing it. And the third method, of course, that is this foolproof method. On one condition, you can go back and redo it, resurvey. If I could go back and measure it again without the condition changing, then well and good. For instance, a concrete column, indoor concrete column with, I miss that. I go back to the slide, measure it's still there, well and good, no problem. But I want the temperature at 3 o'clock yesterday. I can't do it. I can't even go back and measure the temperature at 3:45. Now it's 3:47, for instance. I can't. So example. So it's a perfect way, it's the best way to fill in the blanks for missing data, but it's not always doable. Even if it's doable, it is still time consuming. So my dear students, the idea here is that while we can always go back and redo, the experiment, redo the measurement, try to avoid leaning on that or incline towards that. Weigh all your options. When there's nothing else you can do, then only go for the redo, because it's the easy way out again. I mean, it's not making us think of how to resolve the problem, or just going back and just keep turning the mill and churning out the data again and again and again and again, without trying to think what went wrong, why is this data missing, or why is this data an outlier? You get what I mean? Yeah. So avoid jumping immediately to redoing the test. When something weird is popping up in our data. All right. Apart from time consuming, labor intensive, and all, it is really about our our skills. All right, our skills and our ability as a researcher. All right, train yourself up in that. And finally, the third step is data coding. So this is where data analysis, I'm trying to put in a meaning. Like I'm trying to group and assign meaning values to my data now. For example, I have interviewed 1,000 people. I want to see what's the average age of their respondents. All I have to do is to create the age bucket. So probably this is like the whole community I interviewed them. So there'll be kids, there'll be primary school children, secondary school children, there'll be tertiary education students, there'll be retirees, there'll be working adults, and so on and so forth. So I could probably put them in the age brackets of 16 to 18, group 1, 18 to 20, group 2, and so on and so forth. So when I look at my data, this 1,000 data, I can start categorizing them into these respective categories. So it wouldn't be that much to look at anymore. I can look at them in their respective groups now. All right. Good. So now we try to look at the methods that we can use to conduct quantitative data analysis. It could be descriptive, it could be inferential. So if we are talking about descriptive, then just like we have just discussed earlier on, all those common statistical terms called the mean, the median, the mode, percentage, the frequency, range. But if it's inferential, we are really looking for a relationship. Why? We try to generalize the results. This is a relationship between y-axis and x-axis, meaning between these two variables, these two parameters. There is a certain pattern, even though there's a scatter, all right? Or it's a linear plot that can take through and cut through all these data points at say 93% of confidence level, 0.93 coefficient of correlation, then meaning that if I have a data coming from a data point coming in, 93% of the chances is that it will hit my regression line. Yeah. So that is what it's about. Making an inferential analysis. Okay. And if we are doing descriptive statistics, and the first step is really to summarize the data and find some pattern there. So where we talk the mean, median, and so on and so forth, those are very direct, right? You quickly can find that. And then we start looking at absolute numbers, right? What exactly it is. You do not explain the rationale, but it gives you a number first. Then only you try to explain the numbers away. Now, a percentage, for instance, is a good way. Increase by percentage or reduce by 100% or ratio, all right? Then only we go into explaining these results, these numbers that has come out from your particular sample group or sample set. And you have 1,000 samples, remember? You've broken down them to 5 groups. So each has got 20 in each bracket. So every group will have their unique individual analysis coming up. So each group will deserve your descriptive description there. And after analysis is done for each group, then only you look at the comparison between the groups. Can you see that? So it goes small and then it goes big. So you go near, you go out, you zoom in, you zoom out. And that's how you should be looking at data. Otherwise, you try to look at 1,000 data, it's going to be a nightmare. And it's going to lead to nothing because it's just too random and too wide. All right? It can be anywhere now. Okay? And if we talk about inferential statistics, and we are talking about the next step, helping us to make conclusions or to make some predictive models now. All right? And to see if this model is being applied to a similar population or a greater population. If it applies here in for the Johor contractor class B, would it be applicable to the contractors class B in Malacca, in Kuala Lumpur, in Penang, and so on and so forth? Can you see the pattern there? Yeah. So as long as you are still within the context of Malaysia, for instance, then most likely it's going to be the same. Well, if I take this model and try to fit into Indonesia or in the Philippines, maybe it's not quite correct now. Maybe it's going to be another line coming into my plot, right? Because it could be cultural difference. It could even be climatic differences. You get what I mean? Policies, respective countries, so on and so forth. So this is where we try to use inferential statistics to understand the larger population, but still within a certain context, certain boundaries. Otherwise, the prediction you're going to make is irrelevant. Okay? And there are two main uses. You want to make estimates, or you want to make some test hypotheses to see whether your conclusion you want to draw is going to be something that is for it or against it. Okay? And it has to be when we do this inferential approach, we have to make sure that the sampling that we execute is random, unbiased. Otherwise, it is not going to be representative of what you want to investigate. All right. I want to examine, and this is a study about the Class B contractors in Johor, for instance. But when we look at contractors in Batu Pahat, when there are 9 provinces, 9 majlis, 9 different councils in Johor, and I look at only Batu Pahat, and I say that is representative, that is not true now for Johor, because you only look at Batu Pahat. I'm pretty sure that Batu Pahat is very different from Pontian, Pontian is very different from Johor Bahru, right? Even the locality, the access to the resources and so on and so forth are very different. Even their market, the nature of their market is very different, for instance. Okay? So example given here is that you want to select a sample of Form 3 students in Johor and collect data on their PT3 score and so other characteristics. So you could do that, or where would this student be? Which district in Johor, for instance, or which kind of school? Even zoom into Batu Pahat, is it an urban school, suburban school? Is it a special needs school? So it's going to make a lot of difference there. Okay? And next, look at the sampling error. This is where if we don't do our sampling correctly, then we may be getting into the trap of making errors from sampling itself. Haven't even started any analysis, just the sampling itself. So this is something that we have to pay attention to. So probability sampling, for instance, maybe a picture speaks 1,000 words here. Every member of the population has a chance of being selected. So the produced results as representative. It makes sense, right? The more people, or if it's a sample are people, the more units I can hit, I can measure from a group, then the more real, the more representative my result will be. Make sense? If there are 10 apples in the basket, I pick one, and I happen to pick the one that's rotten, and I say this basket is filled with bad apples. That is not very representative, you see? Not even fair. There are 10 apples in this basket, I pick 2. And it happens so that both I pick are rotten. Then I say the whole basket is rotten. Or I should be saying, out of this basket of apples, 2 out of 10, meaning what? 1/5, meaning what? 20% is bad. It may be the third apple I pick up is also bad. So actually it's more than 20%, right? Yeah. But if I can sample 2, then that's all I can say. So you see the danger of us running our analysis based on samples that is not representative of what is truly is. Okay, so let's take a look. The simple random sample method is that I just skip as I like. I just pick. Can be anyone, right? If I'm more systematic, I skip every, I have certain intervals. For instance, I do the first person, I skip 2. Then the second person, I skip 2. I always skip 2. There's a certain pattern to it. Or I do stratify. In that, in this case, for the first tier of people, for instance, area 1, I take the first person in the first group and then the second person of the second group. When I go to the next community, the next group, I pick the second of the first group and then the first and the third of the second group. So it seems random, but I stratify. So when I hit the third layer, I go back to the first pattern here. So it could be I go back to first from the first group and the second from the second group. Or the cluster method. I pick a cluster of 3. Wherever I go, I need to pick a cluster of 3. So there's a certain parameter. So you take a look at these, my dear students, no matter how we do it, there is still bound to be errors. I wouldn't say error, bias, because we are not sampling everyone. We are not sampling every single unit. All right? We are looking at the population and try to pick samples to represent the particular group, the particular community, the particular bulk sample. You get me? Yeah. So there'll always be the error of margin, the error of doubt, the bias margin there. Okay. If it's non-probability kind of approach and sampling method, then we are talking about based on non-random criteria. I do not randomly pick my sample. There's a reason why it's being picked. All right, I always set certain criteria. For instance, if I'm collecting rock samples from a rock core, anything less than 10 centimeters, I will not consider for testing. So I only pick out those that's 10 centimeters and above. Or I want to be on the safe side, anything less than 10.5 cm, I will ignore. Consider broken fragments. So 10.5 and above, I will take out and put one side, and these are the ones going for testing. The rest are not being tested. Does it mean that the rest are not part of the rock? No, it is part of the rock, but they are not meeting the criteria that I have set down for me to do the sampling. Can you see that? Yeah. So I set down the rules first. So for example, a convenience sample, I will say that I pick one, all right, say this is a population situation, human being. I pick one person in the community and then you pick those directly related to the person. So maybe only the siblings, the children, the parents. See, that right? Nobody further than that. Or it could be a voluntary situation. I go down to this committee, anybody willing to answer my questions. So people who agree will come to me. And it could be anybody. It's really very random now. Or it could be purposive. I go to one person, all right, and this particular person has a relationship to a cousin, and yeah, my second cousin, all right, this is my uncle. Oh, this is just my neighbor, not my auntie. This is my auntie. So still, it's like, there's some kind of relationship there. Okay? Right? Or snowball sample. These are MLM, the multi-level marketing strategy. I get one person, you find two people, and the two people, each of you find three people. So it goes down there. Again, there could be some bias there. It could be that when I pick this person, the first sample that I pick, I say, you are the head, you are the kapla, now you go and find two more people to answer my questions. This guy is, say, he's a biker. So he will be asking who? His friends, most probably the people he hang out with are also bikers. So these two guys are also bikers. So if the question there is going to be like asking about, do you agree that riding superbikes is a noise source of noise pollution? They most probably will say no. Yeah, that's what I'm saying. Okay, no offense to the riders, yeah, this is just an example. And then these two people, the green and the blue, most probably will be asking friends who are also bikers. So the answers to my questions now, my survey is going to be pretty much biased now towards the bikers community. That's why we say there's no foolproof way. Yeah, like this, there's no foolproof way of running our samples, doing sampling. Somehow or other, there'll still be some error creeping in, inevitable. Okay. Next, we look at hypothesis testing. So this is a situation where we try to um, compare the populations and to assess the relationship between the variables using the sample. So each group that we assign, they have done the analysis. Well, no, now is there some kind of similarities, some kind of differences? What kind of factors are causing the differences? What kind of factors they share that cause the common, they share the common traits, common characteristics? What are these? And this is where we also try to identify and estimate the possible sampling errors, all right? And could be parametric, could be non-parametric. And if it's parametric test, that's better because there can be more, it is statistically more powerful, because it can detect a defect or something that's weird if it's there. Okay? Example, we like to do this, the distribution curve. We do this. We learn this in Form 1 mathematics, I think. No, I'm talking nonsense. I think in Form 3 in the statistics chapter. All right. So we can look at these. Now, the normal ones are the normal distribution. So we know this is the mean, median, and mode overlapping on one another. Correct. But if it is skewing to the right, then I know that my median is somewhere to the right, and my mode is that, of course, mode is the highest point, but my mean could be very far from my mode. So the mean value could be very low, right? Because it's a graph that's skewing to the right hand side compared to the mode. But if it's a skew to the left side, then my mean could be very low compared to my mode. Can you see that? So that is why it is very important. It's very, very important when we're doing inferential statistics that the way our data is being analyzed and the way we interpret our data. Just by looking at the 1,000 data, remember the 1,000 data in a set, just by looking, staring at it, it's not going to give us any answer. The answer will only come when we begin to turn them into graphics, if you like. Graphics are not cartoons or comics. Our graphics for the engineering people, they are graphs. Graphs a picture that tells you 1,000 stories. All right? Very good. And I think this is the last one to show. We like to do this. Yeah, scattergram, no problem. I put in the regression and that's it. Don't forget, when we put in the regression line, best fit line, that's what I say. Put in the R-square value. The R-square value is the coefficient of correlation. It has better be 0.95 and above, meaning that 95% above, meaning that anytime I got a point, I drop it in, 95% confidence is going to drop on my line. If it is 0.7, meaning that if I have a point coming in, 30% chances is that it won't hit that line. If it's 0.2, meaning that if I've got a point coming in, there's only 20% chance it's going to hit that line. What good is my model if the predictive power is only 20% accuracy? You understand what I'm saying? Yeah, so always put in the R-square value and ask ourselves, what is acceptable? If you think that 0.9 is acceptable, plus minus 10% error is okay for you, then go ahead. But explain it very carefully. Because this error margin, acceptable error margin, it is highly dependent on our project nature. If our research is very strictly adhering to the standard prescription, JKR standard for instance, then we have to abide by the standard given values, the limits given there. And you can't, for the front of it, for instance, CBR value in road building, 95%. For the sub base, for instance, then it has to be 95%. I can't be saying I want 90%. No, it's 95, it's 95, for instance. Okay, got that? So very quickly, take a look at these figures you see here. If it's rising to your right, going up towards the top right hand corner, it's positive correlation. Going down, it's a negative correlation. If it's like this over the place, like, no, there's no correlation. Don't force it, okay? Right. And once we got that in, then you see that there is a graph, for instance, weight against height correlation. You see that you can put in the equation now. Remember, if you're using Excel, Excel only gives you y equals to what x plus what c. You have to change that into what is your y. In this case, the y is your weight and your x is your height. So make sure that it's being changed when you transfer that plot into your thesis in the Word format. Don't use y and x. That shows we are very careless. Yeah, we are careless then. All right. There you go. Okay. Thank God. So I haven't lost my voice. Thank God. And we are coming to the summary of things now. I think I'll just wrap it up and then you can ask me questions if you have any, okay? So the long and short of it is that in doing your research, to make sure that our basis is always strong, okay? To make sure that our engineering research basis is strong, some points, make sure that the research question is very clear. We know what we are seeking out there. That means our problem statement is very, very clearly defined. No problem statement, no question. Am I right? If I don't even know what the problem is, I'm going to pose the question to resolve. Right? Solid theoretical foundation. And if I'm going to do investigation on the slope failure induced by rainfall, then I'm going to use slope failure analysis models, right? Analytical approaches. So I got to decide whether I'm going to do a slice method or I'm going to use this slope that I'm talking about, going to be the infinite slopes. So these underlying theories must be in place right from the beginning. Methods, what are the tools, what are the measurement methods, the analytical software that I'm going to adopt in my study to answer the question that I pose for myself, right? Accurate and honest data collection. I especially kept the honest data collection, the honest bit, because we got to make sure that we are being ethical, right? What good are we? We are doing postgraduate research here, master's or PhD. Postgraduate, already graduated. Congratulations, already got your bachelor degree. So postgraduate meaning that I graduated, but I'm going for continuing education for myself towards a master's or PhD degree. So already a mature student, already you are a responsible scholar and growing to be a good researcher. Surely we can train ourselves to be highly ethical and honest in our data collection. It's wrong, it's wrong. It's an outlier, it's an outlier. It's a missing data, it's a missing data. We do not create or manipulate our data so that our graph looks nice, right? Reliable and repeatable data collection analysis, we follow a certain standard procedure. The best practices, if it's a procedure is not in the standards, it's something that's prescribed because it's certain equipment, special equipment, we follow the manual of the company, the manufacturer. By all means, just state it very clearly. If this is the make, this is the manufacturer, this is the model, then this is the procedure. If there are certain modifications that we have implemented because of the limitations of your work and so on and so forth, or requirements of your work, make sure it's being mentioned in your method chapter as well, your method statement. All right. And then good organization, documentation, and presentation. Always make sure that the data, your information, even your literature is being organized accordingly. I know these days youngsters do not like hard copies. Unlike me, I probably belong to the dinosaur section of the museum now. I still like hard copies, but I appreciate recycled papers, okay? But it doesn't mean that I kill the forest. I totally support reforestation. It's just that it's a lot easier to read a hard copy, a printed out a work, and to mark on that than to use a stylus on the screen. That is my personal opinion. But in your case, whatever you do, just make sure that it's properly organized. All your documents, your data, your referred paper, and so on and so forth. Even your own writing, drafts after drafts, your graphs, your simulations. If you run software simulations, where you keep those data, and for instance, you run proxies, they are very big files, heavy files. So not ordinary computers can run them. And after a certain point, you may find that your computer is slowing down. So I need to upgrade the RAM of my computer, or I need to, I don't know, do something about it. Or I need to start saving stuff in the cloud and stuff like that. And then it goes on to about data security and all. So you need to consider all those as a good researcher. Last but not least, transparent reporting with evidence-based report. Always evidence-based. A research report, the thesis, is always talking about evidence. It's not good enough. You say, she say, I say, not good enough. It has to be evidence-based. So, supported by what? My own data, my own observation, or data that is being extracted or inferred from other people's work. All right. And make sure that you stay calm, stay cool, stay organized. You have version control thesis. I'm sure after a while, we have many versions of draft 1, draft 2, draft 2A, 2B. So just make sure you know what's going on. Doesn't matter what coding you use for yourself. If it's a collaborative writing, these days you probably use latex and I forgot what's the other one. Whatever software you use to help you in your organizing your figures and so on in your writing. By all means, just make sure that you know the tools well to use them correctly. Oftentimes, for instance, I have students using Mendeley to organize their citation references, but the reference list is a mess. So please don't let that happen. All right, you still have to double check while the AI has done it for you. Project planning, make sure that you keep time. Data storage, safekeeping of data, always retrievable. And keep calm and keep up the good practices, like a lab notebook is always good. When I say a lab notebook, it's a logbook. I'm talking about hard copy thing. It's up to you. If you think your lab is clean enough, especially those dabbling with microelectronics, your lab is super clean, the clean rooms, right? So there's no issues. For us in the civil engineering area, we play with soil, play with water, contaminated soil and water for the matter, concrete, and also those are dirty stuff. You don't want to be bringing a tablet around, I guess, with your hands dirty and all, and the dust and all. So you may want to bring just a hardcover, traditional pen and paper kind of recording to jot down and to sketch stuff when what things that are going on in the lab with your dirty hands and all. So those stuff then a lab notebook will be necessary. And make sure you back up data regularly. If you are logging your data, all right, thank goodness there's a logger to log data. Make sure you download and update the data continuously, even though it takes a week to finish a test and odometer test. But every day the loading stages will be the loading stage will be changed. Make sure you download and keep the data in a safe place and start processing them if you could. You can, I mean, don't wait until the very end, because if you wait right up to the very end and the experiment takes 1 week to complete, if there's an error in this setting up of the test, you have wasted 7 days to come out to the last day to realize that there has been a mistake in the setting up from day 1. If you check on day 2 and realize and notice that outlier and trace back to a wrong step in the setting up, you will have terminated the test and started the test on day 2 itself. Am I not right? And save yourself the remaining 6 days. Time is of essence. And your document coding and simulations and clear naming convention. That is why it listens to very important. Always keep time. You have planned your Gantt chart, follow your timetable. Then what's the point of making a plan when you're not going to stick to it, right? That's why I make a plan that is realistic, that you can do, and not someone else can do, or not your supervisor like it. All right. So the summary of it is that research means you don't know, but you're willing to find out. Make sure we start by saying that research is about doing something like that we don't know, And then hence we are finding it out. So it's an adventure, if we like. Think of it as an adventure. Okay, we don't know. It's like what Newton said. Every stone that we is like a boy walking along the shore, the beachfront, and then every stone that every pebble that he turns over, he don't know he's going to find. Of course, it's a modified version of what he said. Roughly, it's like this. You got as a researcher, you got to be thorough. It doesn't mean that I only pick up the big stones, the small one ignore. A lot of times, the small ones are the ones who give you that major discovery, the big, significant, impactful contribution from your work to the existing body of knowledge. All right. So with that, my dear students, Professor, thank you very much for your attention. I hope this about 2 hour and 15 minute sharing will be helpful in your work. And if you have your research proposal development stage, it will be helpful for you to do that. Or if you are already well into running some prelim tests, it will be a good reminder of how one of the common mistakes that we want to avoid and leading to better data analysis and data presentation later on. Okay? Right. I think there are some questions here, so let me see what I can do here. I want to see my chat box. Is that right? Shall I? Where is it now? Oh yeah, here. It's lagging. I think the attendance form has been circulated, so make sure you fill that up to have your attendance taken down. All right. Let me just see if there are any questions. I don't know if I can scroll up there, but if you don't mind, if you could just turn on your mic to ask me the question if that is all right with you.
Good evening, ma'am.
Yep. Hello.
Hey, so yeah, good evening, ma'am. Just we need the assignment date to be extended a little instead of 8th December. Can we extend a week more? Or the
Are we going to
assignment?
assignment now? Can we talk about the assignment after this, after the question and answer session? If there's any question, then we go to the assignment. Is it okay?
Okay, okay. No issues. Thank you.
All right. Thank you, Aziz. Is there any questions you want to ask me about about the research methodology? Anything at all? No? No questions? That's good. That's amazingly good. Or if there's no question, then let me take you through the assignment, all right? Well, Azil, I don't think you need more than a week to do this. In fact, I think you can finish it by tomorrow. I try to make it minimal disturbance disruption to your research work because for everyone has been through this before. It's compulsory for all of us to go through research methodology class, and there's always assignments coming through, of course. Otherwise, no assessment can be made, right? So I try to keep this as minimum as possible, keep it to the minimum disruption to your work. As I say, it's a mini assignment. So let me take you through it. Then maybe you can tell me whether you really need more than a week to do this, okay? I would like you to submit a mini research plan for an engineering problem. So just take it from your research project you do. Maybe is your research project is a very complex one, maybe just a small part of it, maybe just one objective you do, for example. Because this exercise, as I said, is just to a practice, an exercise to see that we are on the right track in designing our own project. That's all. All right. I am not your supervisor. I'm not of your an expert in your field of study either. So I'm not going to look at the content. I'm going to look at the research plan as a whole. All right. To see whether you got the right end of the stick, if you like. So the objective of this small assignment is that you apply the concepts of the research methodology to a real engineering topic without actually running any measurements or experiments. You propose a clear, structured, and well-justified plan. So choose one problem. That's it could be one objective of your bigger problem, bigger project, any of these areas, because you come from different engineering fields, right? And just a one page mini research plan. One page, not 10 pages, yeah? Only one page. So there are five components that I need you to have in your one page, A4 size, not A3 size, okay? Research problems objectives, define your problem, provide 1 or 2 research questions, 1 or 2 is good enough, and explain the importance of it. For instance, if it's a problem for industry, how does it affect industry if this problem is left untended? Second, look at the theoretical simulation and from the framework, right? Describe what theory, what is the underlying theory, principles, simulation you're going to run if you do it. If you don't do it, you go straight to experiment. By all means, just say the simulation bit is that this is how you plan your experimental work. Then you move on to the experiment, the test setup, the measuring tools, the devices, so on and so forth. Three, the design and sampling. Whether it's experimental algorithm, is a field measurement, the sampling approach. Where, how frequent, how many? Is it affected by the season? Is it all year round? Or is it non-affected by when you take it? All right. Data collection and analysis plan. What are the quantitative data you expect to be coming out that you're going to produce for analysis? Qualitative data, if relevant. I say if relevant, as of course we already said this again and again. Most engineering programs, research projects will not be what do you call that? Will not be based on qualitative approach. And what about the analysis method? Surely you already have in mind what kind of softwares you're going to use, and what are the expected challenges, and how you plan to handle them. For instance, you want to use ANOVA, we have no experience at ANOVA. Do you know where to get the ANOVA software? Can you get it at a student price, or is there somebody who can teach you? Is there a training program you can go for, a short course, or how much does it cost? Can you afford that? Can your supervisor help you with that? Things like that. Okay. So while this is a mini research plan, I hope it's also a real one for you. Okay. And last but not least, research management and tools show that just write down how you're going to organize your files, and how you code examples of how you code name your files, for instance. Is there any collaboration tools if it involves other people? If, for instance, you want to work with industry, how do you keep the communication channel open? And what about the version control and documentation plan of your own thesis writing? Is that do you go by year, a folder or year, go to 2025, 26, or no, I go by version 1, version 2, or every time my supervisor return me, I consider if this is draft chapter 1, draft 1A, draft 1, my supervisor return become draft 1B or what? So how do you do that? You certainly have to come with some system for yourself, because otherwise, as time goes on, as your thesis builds, you find that you get confused. All right. Do not override them. Keep them there so you can go back and refer to them. All right. And what do you expect to be submitted? 1 page. I cannot emphasize enough. Yeah, 1 page. Just a 1-page mini research plan. I imagine it could be a mind map. Right. Any format I don't mind, as long as it's just in 1 page, not more than 1 page. All right. A simple diagram of your proposed methodology. Usually we have a flow chart, right, showing what are the steps that you have to go through to come out to the final reporting. And there's no need to run any experiments and simulations or coding. No. Just a plan. All right, just a plan. And to be fair, the way the assessment is going to be run is being written down here. If you look at it carefully, it's actually following through the 5 items that we have just talked about. Okay, and submission. I think you jumped to this and saw the 8th December. You didn't look at the instructions yet, and just make sure that it's PDF, right? So that when I open it up, it's not being disrupted, and all your hard work going into a mess. And please save your file as your name. Just for instance, my name. Put your surname, all right, and then your first name, your second name, in brackets, your metric number, all right, underscore M3. This underscore M3, so I know this is for module 3, so we don't get mixed up there. Okay, so it's just a single page thing. And considering that, my dear student, tomorrow we won't have class. I was hoping that I could finish up today, so thank God we did it, that tomorrow at this hour, you can use the 3 hours to do up this small assignment. So it wouldn't be a burden to you, meaning that if I were with you face to face, this would have been an in-classroom assignment. No burden, no extra work, no stress. Is it okay? Who was the one who asked me questions, who asked for extension? I hope this is acceptable. All right? 8th December, I believe many would submit by tomorrow. Okay, so tomorrow afternoon, I won't be seeing you. We have no online class. We have completed our lecture, if you like. So tomorrow afternoon, you're supposed to use that 3 hours to do this assignment. Okay, it's an in-class assignment, so that it will not burden you later on. Right? So I hope this, let's take this as the first step in time management. We use the time allocated for the class for a certain task for that task, so that we can come out of tomorrow, completed module 3 done. Submitted means done. I believe nobody will fail. Okay? Understand? Is it okay? And all these are already uploaded in the shared folder. Yeah, you can get it off there and start working on it. Okay, any questions? Any questions at all? Understood? Good. Right. If beyond research methodology, beyond today's discussion, is there anything else I can assist you with? Is something else you want to ask me about? I don't know. Something that is a generic question about your research or just wanting some opinion, advice. Is there something I can um, assist you with? Then by all means, please shoot. Mm. Since you are ahead of time. Anything? Mm-hmm. No?
Hello, ma'am.
Yes?
Hello.
Yeah, yeah.
Yes, ma'am. Do you have to add the graphs in this plan, or just we have to mention that what would be the our methodology, or what type
You
of the
can,
software we are using?
if you think putting an example graph, just a sketch of it, is easier to explain, then by all means, all right? Anything goes actually. No fixed and fast rule. As long as you know what you're doing, and I can see that you have a clear idea of what your research is all about. This is research plan anyway, so that is good enough for me. Okay.
Hi, ma'am.
Yes.
Can the assignment I do related to biodiversity because I'm from FAS, I'm science student, so I'm not an engineering student. So can I do related to that biodiversity?
Sure. The thing is, I would like this small assignment to be useful to you, meaning that do per your project. Don't
Okay.
create something, yeah, just do but per your project. I'm sorry, yeah, there will be science students here as well, apart from the engineering students, right? So true, just go for your own project, and I'm sure uh the criteria set out for this assignment is the same whether you are from engineering or science background. Okay?
Okay, thank you.
All right. Hmm. Anything else? Anything you want to clarify? No? Well, if no, then I guess we can wrap up. I don't know, is Dr. Hadila here, or is there someone from CGS here? Yeah, Dr. Hadila. Yeah. So doctor, can we wrap up, or do you need to say something to wrap up the session? How does it work? Or take a picture or something? All right, so if you could, please, we'll have a picture taken just to commemorate the moment. Many of you I probably wouldn't meet in my on campus, but when different campus, some of you probably spend most of your time in your home country or hometown doing your study remotely. So that'd be nice. Okay, done? Right. So with that, thank you very much for being here, listeners. I wish you all the very best for your respective studies, whether it's master's or PhD, full time or part time, on campus or out of campus, in the industry or beyond the industry, and so on and so forth. All the very best. It has been very, very courageous of you to embark on this journey in the first place. We are going to the unknown, remember? We are going to something that we don't know, and yet we want to find out the answers. So have a good adventure, stay safe, and if you want to reach me, I guess you can get my number from Dr. Hadila. All right. So all the best. Ciao. Take care. Salam.
Thank you, Prof.
Thank you.
Thank you, Prof.
Thank you, Prof. Thank you.
Thank you, Prof.
Thank you, bro.
Thank you,
Thank
Prof.
you,
Thank you,
Prof.
Prof.
Thank you. Bye.
Thank you, Prof.
Thank you, Prof.
Thank you, Prof.
Thank you, Prof.